Alright, so today I want to talk about a pretty nice theorem in Fourier analysis. It's actually a pretty fundamental theorem and it's very applicable to physics. And at the end, maybe we'll talk about some of the applications. Alright, so just so we're all on the same page about notation, we'll say that, we'll say that chi of t is e to the I 2 pi over n t, right? And today we're going to be working in the discrete case, so we'll take our space to be z and d, right? Okay, and then we'll say that if we have some function, let's say f, which maps from our space into the complex numbers, then we'll say that the Fourier transform also maps from those two spaces, and we'll define it to be f hat of, let's say, m equals n to the negative d, sum over the entire space, z and d, of chi of negative x dot product m times f of x. Alright, so pretty standard notation there. Okay, so basically what we're going to talk about today is we're going to try and get some relation between the sizes of the support of f and its Fourier transform. Alright, so let's just say that we have this function f exactly here, and we'll just call the support of f to be x, and we'll call the support of f hat to be w. Okay. All right, so we have another nice theorem called Fourier inversion theorem, and maybe I'll prove this in another video, but basically what Fourier inversion says is that we could write a function in terms of its Fourier transform. So we could say f of x equals sum over all the entire space, so z and d, of chi of x dot m, notice no negative sign there, of the f hats, the Fourier transform. This is a nice theorem. Yeah, maybe we'll prove it in another video. All right, so from here, it's actually pretty straightforward. We're just going to apply Cauchy-Schwarz to this, and what Cauchy-Schwarz says, if you don't remember, is that, well, if we have two functions, right, or sequences of numbers, then if we're summing over them, let's say, ai, bi, right? This is less than or equal to the sum of ai squared times the sum of bi squared to the 1/2, right? So if we just apply this, to our Fourier inversion, this equation here, right, we get something pretty nice, or we get something workable. That's kind of the first step. Cauchy-Schwarz is very applicable. So we'll say f of x. We'll just bring this squared over to this side. I think that will make it a bit cleaner. And so say this is less than, well, we're summing over, we'll look at this as the internal sum, right? So we will say this is less than or equal to, well, we just have the size of the support of the Fourier transform as a first sum times the second sum becomes over m in w of the f hats m squared, right? And obviously w is in z and d, but all of the points outside of w are 0. So we could actually switch this sum over to the whole space. So this is less than w times m in z and d of our Fourier transform, right? And then whenever we see a squared, this is really nice. Whenever we see this modulus squared here, it's really nice because it means that we could apply Poincaré's theorem. And so by Poincaré, I guess I'll just write it. We could also prove this one in another video, but we'll just take it for granted here, is the sum of the f hat squared is just the sum of the f squared. Right. Sorry, p n to the negative d of the fm squared. Right. All right. So we could just apply Poincaré's theorem right here, and we get that this is equal to size of support Fourier transform times m in the whole sum over the whole space of f of m squared. All right, this is pretty nice because if you'll notice, let's see. All right, so if you'll notice here, we can actually change this sum to be over just the size of the support of f, right? The goal here was to be summing over the support of f, right? To be summing over x. Call it x here. And so that's exactly what we could do now because we're summing over f. So all points outside of x are going to be 0. So we'll just switch that sum. So now we're looking at size of w times m in x of f of m squared, right? And this is nice because if you'll notice, this whole side of the inequality, so if we just write the inequality here, we still just have the sum, or no, sorry, we just have the size of f of x, or modulus squared of f of x on the left-hand side. But if you'll notice, this is just a constant, right? This doesn't really depend on anything. It doesn't depend on x, really, right? Sorry, it doesn't depend on little x. Maybe that's a bit confusing notation. Maybe we should have called that something else. Anyway, so what we notice here is we could just sum over both sides, and we'll be summing a constant on the right-hand side, and we'll be summing fx, or f modulus f of x squared on this side. So let's just go and do that, and let's sum over all x in the support. Right, so if we sum over all little x in big X of f of x squared, right? Well, this is just to be verbose, I'll write it out over all x in big X, w times this sum. Nothing changes here, right? But like I said, this doesn't depend on x at all. So this is just the size of x, big X, times the size of w. Oh, I just realized I never carried these n to the negative d's down, but these are all here. Sorry if that was a bit confusing. N to the negative d times n to the negative d. Right, and so this side, these are the same on both sides, so this is just less than or equal to 1. So we get this, and so just to write it a bit nicer, this is the theorem we were trying to prove the entire time. So the size of the support of f times the size of the support of the Fourier transform of f is at least n to the d, right? So this is what we have proven. Right, and so just to write it in another way, support f times the support of f hat is always bounded by n to the d, right? So this is actually a very fundamental theorem in Fourier analysis, right? Oftentimes it's called the uncertainty principle, so I guess Fourier uncertainty principle. And in physics, we see a very, very similar formulation here called the Heisenberg uncertainty principle, right? And basically what that says is that the change in momentum times the change in position, right, is always bounded by some constant, right? And so it's basically the exact same formulation here, right? So if you wanted to prove this, I mean, I don't know exactly how you'd go about proving this, but maybe you could start with a more general case about general Fourier series, which we proved here, and prove that these two things are actually the same. Thank you for watching.